Jai Hind all of you. I'm Dr. Rahul Bansal from Ajay Kumar Girls Engineering College, Ghaziabad. So this one is the next video lecture for the electronic devices KC 301. So in this video lecture, we will be discussing about the BJT common base characteristics, right? So before that, right, we must know about the different operating regions, right? So if you see in the previous video lecture, we have discussed about the active region. So in the active region, if you consider a BJT, right, it consists of like 3 different regions: emitter, base, collector, right? This junction is called as the emitter base junction. Here we have like represented this as like JE, and this junction is called as the collector base junction. Here we have represented this by JC, right? So this JE denotes the emitter base junction and JC denotes the collector base junction, right? So if at all both of these junctions are forward bias, right, then the transistor is said to be operating in the active mode. Let me draw this for you. That is, both the junctions are forward bias. JE, JC, right? So both the junctions are forward bias. The transistor is to be set, it should be operating in the operation. One second. Right, both the junctions are forward bias. It means that transistor is working in the saturation mode. Emitter base junction, that is JE, is forward bias, and collector base junction is reverse bias. It is said to be active mode. Now if at all your emitter base junction is the reverse bias and collector base junction is also reverse bias, under this condition the transistor is said to be working in the cutoff mode. Right, so this is the table, that is mode of the operation, right? So if you see carefully the common base configuration, in the previous video lectures we had discussed about at how to decide which configuration is there: common base, common collector, or common emitter, right? So if we consider the common base configuration, so let me erase the first. So for the common base configuration, if you see carefully, so this is the common base configuration. This base side is common. This is emitter, right? Input is given at the emitter side. And output is taken from the collector side, right? So if we see common base configuration, right, generalized form that we have like discussed, that is, if we consider this 2-port device, this is your BJT, right? It consists of 2 port, input port and output port. Here we have I1, V1, V2, I2, right? If we want to draw the H parameter model, so H parameter model for this is V1 equal to H11 I1 plus H12 V2, I2 equal to H21 I1 plus H22 V2, right? Where this H11 is equal to V1 divided by I1, keeping V2 0, H12 equal to V1 divided by V2, keeping I1 equal to 0, that is input port current equal to 0. Next is H21 is equal to I2 divided by I1, keeping V2 equal to 0, and this H22 is equal to I2 divided by V2, that is transconductance, right? Keeping this input current equal to 0, right? So from here, what we can see is input characteristics for any of the BJT of any of the like transistor. We can draw like this. We can know about the parameter like this. That is, input characteristic is in between V1 and I1, while keeping this V2 constant. It means that input characteristics is in between I1 and V1, keeping output voltage constant, right? So if we see in this common base configuration, what is I1? I1 is IE, that is the emitter current, right? What is V1? V1 is VBE. What is I2? I2 is IC. If you can see clearly, right? What is V2? V2 is VCB, right? Now, if you want to draw the characteristics, right? So, input characteristics will be in between input voltage and input current, keeping output voltage constant, right? So, this is your input characteristics. The parameters are right. So, this is your like VCBE, VCB1 and VCB2, right? Now, for different value of VCB, that is the output voltage, we have the different input characteristics. So, why it is so? It is due to the early effect, that is base width modulation. If we increase the value of VCB, right, see from here, if we increase the value of VCB, correspondingly depletion layer width at the collector base junction will increase more towards the base side. Why it is so? Because of the doping concentration of base side is less than that of the doping concentration of collector side, so that the depletion width will be penetrate more into the base region, right? So, this cause the effective base width will reduce, right? So, effective base width will reduce. So, what we will get? We will get this will be depleted. Now, what is the effect of this? It will cause emitter current to increase. Emitter current will increase due to this early effect. Second effect is beta value increases, right? and a point will come when this base region is completely disappeared. We will have only the depletion layer. At this point, this is called as the punch through or reach through, right? So the effect of this early effect is emitter current increases, that is IE increases, right? So due to this increase in the VCB value, the value of IE will increase. For particular value of VB, we will have the larger value of IE, right? So if we see carefully in this characteristics, right, for particular value of VB, right, which VCB value is having larger value of IE, VCB 2, right? So what we can say from this discussion, we can say that this VCB 2 is greater than VCB 1, right? So this is due to the early effect. Due to this early effect, the characteristics, that is input characteristics, will shift towards the left hand side, right? For the less value of VB, we will get the larger value of IE due to the early effect. So this can be seen from the input characteristics, right? Now output characteristics of common base configuration. From the H parameter model, if you see carefully, right, from this H parameter model, output characteristics will be, if you see the second equation, it is in between I2 and V2 while keeping I1 constant, right? In this case, we will keep this I1, that is the input current, constant, right? So if you see in this common base configuration, right, what is I2? I2 is IC. What is V2? V2 is VCB. Now we have to keep this I1 constant, that is input current constant, that is IE constant, right? So output characteristics can be drawn like this. So we can draw the output characteristics for the common base configuration like this. Right. So this is in between VCB and IC while keeping IE constant, that is this value is for IE1, this is IE2 and this one is for IE3. Right. Now for the different value of IE, we are having the different value of this IC, sorry, this, one second, this is your VCB and this one is your IC. This is IV graph, na? For the different value of IE, we are having different value of IC, right? So this is your output characteristics, that is output characteristics of transistor, right? So if we want to find out the active region, cutoff region and saturation region in this characteristics, right? So active region means emitter base junction is forward bias and collector base junction is reverse bias, right? Reverse bias means this VCB must be, if I consider this as like NPN transistor, So VCB must be positive, right? Under this condition, this junction will be reverse bias, right? If at all VCB is positive, the collector base junction will be reverse bias, right? Now emitter base junction is forward bias. It means that this IE should be greater than 0. IE should be greater than 0. It means that the reason for VCB greater than 0, see, VCB signifies that VCB greater than 0 signifies that emitter base collector base junction is reverse bias, right? IE greater than 0 signifies that emitter base junction is forward bias, right? Under this condition, transistor is working in the active mode. So can you see in this output characteristics, what is the active mode? This one and this complete shaded portion, I am just shading this complete region is your active mode for VCB greater than 0 and IE is greater than 0, right? Next is cutoff region. In the cutoff region, from the previous discussion, cutoff for the cutoff region, collector base junction should be reverse bias and emitter base junction should be also reverse bias, right? So both the junction are reverse bias. It means that this VCB is greater than 0, collector base junction is reverse bias. IE is less than 0, right? IE is less than 0, or you can say IE is equal to 0, right? If at all IE is equal to 0, it means that emitter base junction is also reverse bias, right? So this region is basically your cutoff region. So let me define this. This is your active, and this one is your cutoff. Right. Now, third region is saturation region. For the saturation region, emitter base junction is forward bias. Collector base junction is also forward bias. Right. So, if you see carefully, VCB is less than 0. It signifies that collector base junction is forward bias. IE is greater than 0. Emitter base junction will be forward bias. Right. So, this region VCB is less than 0 and IE is greater than 0. So, this region is your saturation region. Right. So, we have like active region, cutoff region and saturation region. Now, some approximation that we made, that is IC is approximately equal to IE, that is alpha value is approximately equal to 1. Typical value is 0.99. Now, base emitter voltage is 0.7 for the silicon. In the numerical purpose, we take these values. Right. So, this is all for common base characteristics. Right. So, this is how we draw the common base characteristics. Thank you all of you. Thank you.